This first one is just reviewing simplifying your radicals, because today we're going to look at one of the methods for solving quadratic equations is the quadratic formula, which involves a radical. So this is just giving you, that's why this information was in the prerequisite chapter, and we reviewed that like the first day or so, is because it's now a skill that they are expecting you to employ throughout this section. Factoring is also going to be a skill that you could use to solve some quadratic equations. And so again, I'm having you practice that skill. Again, that was in the preview chapter, the prerequisite chapter, section 5. Then finally, I've given you just an expression to work out that involves a radical in these letters. And that expression, as you know, if you set it equal to x, is the actual quadratic formula. And the reason I did this is I wanted to point out a couple of things to you. And this just comes from years of observing errors that students make and trying to think, is there any way I can help you? And so one of the things right away I'm going to do is I'm just going to erase this for a minute, and I'm going to write it a little differently. I'm going to write it like this. So notice, instead of just writing b squared, I've got b in parentheses, and I'm using a color here to emphasize that. And the reason is, if b happens to be a negative number, and we've talked about this, I think, in class 1 or class 2, if b happen to equal, say, as it does later on in your class activities, -6, and you wrote this, okay? Not that you'd be writing blah, 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 but if b is -6 and you're saying that when you square it, this is what it looks like, there's an error here. And do you remember the little, no, it's not imaginary. Yeah, it's the fact that these two things are not equal. When you're squaring a negative number, you must put parentheses around it to say that's the number that you're multiplying times itself. Because this first one, even though these look identical, and this is like just one of those little things that just drive you crazy, this really says -1 times 6 squared. The number that's being squared here is the actual number 6. You square 6 and then you take its opposite, so you get -36. And that does not equal -6 times -6, which is +36. So when you write this, I know what you're thinking, but then when you go from here to there, that's your error. So please, I would say, if you've had trouble using the quadratic formula before because you run into like little errors, just do this for yourself. Just when you write it, put little parentheses around the b, not the b squared, just the b, to remind you. And then you see that for AC, I have a bracket around there. It could be a bracket, it could be parentheses. And that's because of what happened right here in this formula. Now, if you did this successfully, you don't have to think about this. But what happens when the expression for AC is negative is sometimes students use this subtraction symbol right here to replace that negative sign. So they write 81 take away 40. Okay, so the reason I've set this off in brackets is for you to see that this number, particularly when it's negative, is that dash that you put in front of the 40 is a separate dash from the dash you use for subtraction. So that you now call that 81 plus a +40. Now again, if you have successfully worked many times with the quadratic formula, you never have a problem calling that 81 plus 40, ignore what I'm saying. If you've had some difficulties in the past with the quadratic formula because you make what you think are little simple arithmetic mistakes, then this suggestion might help. Okay? Now the good news is that the quadratic formula can solve any quadratic equation at all, any one. So you never have to learn another technique. However, many students mess up the quadratic formula. So today we're going to look at 2 or 3 different methods for solving some quadratic equations. And but to know this will always be your fail-safe method. Okay, you can use this at any point. Nick?
Is it dangerous to, like, since you're taking the square root of something being squared, instead of, sometimes I just look at it as right in B.
No, because it's not this a big subtraction here.
Right.
The square root of b squared minus a squared is not b minus a. It's not a product or a division in there. And since the square root sign is an exponent properties apply to products and division. Nope.
Well, only makes a difference if it's negative.
Nope. It only makes a difference if it's multiplication, like this. Then you can call that b. But if it's this, b squared minus a squared, you can't call that the square root of b squared minus the square root of a squared. It's only, and it's an exponent because it's the exponent 1/2 square root. All your exponent properties apply to multiplication because an exponent talks about repeated factors. So if you had a 1/2 here, you could call that square root of a times square root of b. Or since division can be written as multiplication times the reciprocal, it also applies to quotients. It never, ever applies to an adding and subtracting problem underneath it. Okay, good question. Anything else? All right, so we're going to start off now with the teaching demo. And first we have to cover the idea of complex numbers. And we're just going to begin complex numbers. You're actually going to do the arithmetic with complex numbers as part of your class activities. But this little cartoon here is maybe how some of you feel you want to be on the couch after dealing with this idea of an imaginary unit or number. So this little square root of I is on the square root of -1, excuse me, is on the couch saying, do I really exist? And yes, I really exist. And just like Mozart and Dr. Dre make up music compositions, mathematicians make up numbers, yes. They define numbers. And as long as these numbers hold true with all of the algebraic principles, then, for example, mathematicians back in the Renaissance areas used to have these little competitions, and there was money involved. And they came upon an equation that couldn't be solved with real numbers. So this new imaginary unit was defined. And then from that, another entire number system got created called the complex number system. Oh, well, I know, because it makes you think it's complex, right? Yeah. It's what? Yes, yeah, because it's imaginary, right? That's part of the cartoon, right? Yeah. I know it is a unfortunate name for the number to call it imaginary. Okay, so you're never going to find this in your soul, and you're not going to feel it intuitively. Okay, it's a definition. Just like, there's a definition for serendipity. There's a really interesting place where serendipity came from. You should look it up. But I'm not going to get into that because we got limited time today. But okay, so I is defined. It's a number. It's an imaginary unit. That's what we call I, an imaginary unit, or a number. It's the square root of -1. That's how it's defined. So if you had the square root of any negative number, the way you can separate that radical into a multiplication problem is, again, by doing what you're familiar with. You factor this number, and one of the factors is the square root of -1, because there's a -1 multiplying that k. You could put it right in there if you wanted to. There it is. -1 times k is the same as the opposite of k. And then you'd have the square root of -1 times the square root of k. And then we could replace the square root of -1 with that little I. Now, if k happens to be one of our really lovely perfect squares that we should be familiar with, at least up to 144 or 169, that list of perfect squares, if k was one of those numbers, then boom, you might, so for example, if k was like 121, which you just came across in your preview activities, you could call that 11i, 11 times I. If it's a number that's not a perfect square, like 5, then you would just say I times the square root of 5. Okay? So that's the definition of the square root of a negative number. So let's evaluate a couple of things here now that we've seen that definition. And someone want to help me with at least the first step of breaking down the square root of negative 49, and we'll proceed. I don't want the answer. I want the first step as if you were showing someone for the first time like we did up here. Okay, Jasper? Okay, before I even get to I, I'm like really breaking it down. Square root of negative 1 times the square root of 49, right? And now the i's have it. Square root of negative 1 is I, and I say I to that, A-Y-E. And the square root of 79, 7. Okay? So you can write it like that, or the standard practice when k is a rational number is usually you put it right in front of the I. But again, it's multiplication, the order doesn't matter. I don't care how you represent it. Okay? Any questions on that? Okay, B, we're going to start the same way. We're going to factor out the square root of negative 1, and we're going to write the square root of 8. We're not factoring it out. We're just representing that as 2 factors. And I is represented by the square root of negative 1, and we have the square root of 8. Well, if you had something like that, I would write on your paper, not fully simplified, right? Not fully simplified, because we can simplify the square root of 8 further, because that perfect square divides into 8. So I would write this as I times the square root of 4 times the square root of 2. And I would call that 2I times the square root of 2. The square root of 4 is 2. I usually put the rational numbers as the first factor, I second, and then whatever irrational number as the last factor. But as someone asked me in my first class, does it matter? It doesn't matter. You could say square root of 2 times I times 2. Doesn't matter. Okay? You could say I times 2 times the square root of 2. Lots of potential. Okay, so when you have a number like this, a square root of 4 times the square root of 4, what's your answer? 4. Square root of anything times itself, square root of anything is what? Anything, right? Right? So I square represents I times I, and that says the square root of negative 1 times the square root of negative 1, which equals negative 1. So for our purposes of what we really are doing in Math 107 and what you'll be needing for your arithmetic that you do with complex numbers, like when you multiply them, when particularly, this is like the only power of I that you need to know. You need to know what I is. I is the square root of negative 1. And you need to know that I squared is negative 1. So that means later on, if you come across an I square, you can simply replace it with a negative 1. Yep.
Wouldn't that one be positive?
Nope. Nope. Because this does not apply when your radicand, which is a number under the square root, is negative. You must simplify them with your eyes before you multiply them. Right? So this thing that you're used to, Ramsey, when you're used to seeing this, the square root of A times the square root of B, and you're used to putting it all under one radical, that does not apply to negative numbers like we did over there. Okay, because it's an even root, Ramsey, and you can't find the square root of a negative. So you don't want to turn it into, if you multiply these, you'd get the square root of 100, right? Right. And that's 10, and there's no way 10 is the square root of, has anything to do with the square root of negative 20 and negative 5. You've got to see this as separate from the properties you were working on when A and B were positive. All right. So that's why I have that highlighted already for you, that if the radicand is negative, we write the radical in terms of I before we perform our operations, okay? So when you see something like this, the square root of negative 20 times the square root of negative 5, what you want to do is you want to simplify each one first, and then in the end you do all your multiplication, okay? So this first one becomes the square root of negative 1 times the square root of 20. That's my first form of simplification. Ramses, if you skip a bunch of steps and you come out with the right answer, but there's a lot of steps here, and if you come out with the wrong answer, I can't give you any partial credit. And if it's a take-home quiz, you have to show me the work because you could have called your friend up and just gotten the answer. It says very clearly on all those take-home quizzes, you have to show all your work for credit. I wasn't born yesterday, as I tell my 16-year-old. Okay. Nope. Very long yesterday. All right. So again, could you skip this step? Yeah, you could probably do this. Maybe. I don't know. I can't talk for every single one of you, right? You're all in different places. So you've got to do what you got to do. But you've got to show some work, even if it's one step before the answer. Now, this is multiplication, so I'm going to write these things like this. I've broken up 20 into the square root of 4 times the square root of 5. And now I have an I square there, don't I? So what do I replace that I square with? Negative 1. I square is negative 1. Square root of 4 is 2. Square root of 5 times the square root of 5? Square root of 25 if you want, Ramsey. See, you can say that now. All right, the square root of any number times the square root of that number is the number itself, 5. So my answer here is negative 10. Okay, it's negative 10. So if you don't feel comfortable saying the square root of 5 times the square root of 5 is 5, I mean, think about it. This would be if you had a square of area 5. Each side would be the square root of 5. So anyway, if you have to, you could say the square root of 5 times the square root of 5 is a square root of 25 and then call it 5. If you have to do that, that's okay. Right, any questions on how we get negative 10, Rose? No? The square root of negative 1 is I, because that's how we defined it back here at the very first step. I is the square root of negative 1. So that is, you have to memorize that I is the same thing as the square root of negative 1. That's how we define it. So where I see the square root of negative 1, I put I. And over here, I have another square root of negative 1. So I have another I. I have two I's. And that's I times I. And I times I is I square. And we just defined I square to be negative 1. Yeah. So these two things right here, Rose, these two ideas you definitely have to have memorized. And you know what? You're going to use them so much you won't have to worry about memorizing them because they'll become very familiar quickly. Okay? Yeah. Julia, did you have your hand up over there? Then that's fine. Cube root of a negative number is a real number, so you won't have to use imaginary units. It's only even roots that we have to worry about. Ramses? Why is that out? Why is that out? Okay. He's not. He was trading stocks, wasn't he? Yeah. Any insider information? Ah, shoot. All right. Okay. Go ahead. Back to your question. All right. I don't know what the cube root of I is. I don't. No, I don't. I'm not giving you a hard time. The only thing I know of is what the square root of negative 1 is. That's I. So I don't know what I can multiply times itself 3 times to come back to I. All right. I know what I cubed is, but I don't know what the cubed root of is. All right, well, I think we could answer that. Yeah, let me just shut this off for a second. About quadratic equations. Start us off here. Who am I going to pick on today to read? Nicholas. Yeah, please. Okay. Thank you very much. Okay, so this term right here, first degree, and then this term, second degree, could be new to some of you. Both linear and quadratic equations come under polynomial equations. That's a big umbrella name for classification. These are special polynomials, linear and quadratic. So equations. So their big umbrella group would be polynomial equations, and those would be things to any power. But once we know that the power, the biggest power we see on x or whatever our variable is 1, we call it linear. Because if we were to graph it, we would, if we set this equal to y, we got our x terms and our constants on one side, and we set it equal to y, it would be a straight line. So that's why the word linear. Now, we don't call them parabolic equations, which might be helpful because the shape of a quadratic equation is a parabola, but we do call them quadratic, and that means the highest power you see is 2. Sometimes it's your x term. This is a term because it has an addition sign here. Just x is being squared, but sometimes it's a quantity like x minus 7. Okay, so if I were trying to solve this equation right here, this is just a little, the first thing I would do is I would get rid of that coefficient. That's the first thing I do because I like seeing my squared term, whether it's just a single variable like this, x, or whether it's a quantity. I'd like to have that on one side and, if possible, just the constant on the other. So if I had an equation like this, I would divide both sides by -2, and then I would have this to start working on. Okay, but we'll talk about something like this a little later. Why do you think they have to say that if this is the general form of a quadratic, why do they have to tell you in the definition of the general form that a isn't 0? Why do they bother to do that? When you say it will go in the denominator, what do you mean? Well, if you use the quadratic formula and you had 2a, yeah, there'd be a 0 down there. But suppose we didn't even know anything about the quadratic formula yet, and we just saw that as the definition of the equation, and we say a isn't 0. Jasper, I didn't hear what you said. All right, but we're not looking at a line here. We're looking at a parabola. Nick?
Well, it would make it so the wouldn't have 2 as an exponent anymore. 0 times x squared.
Right. If I put a 0 in here for the a, what does this get simplified to? That's a 0, and then I just have bx plus c, which is a linear equation. So if a was 0, I wouldn't be looking at a quadratic equation at all. I'd be looking at a linear equation. So let's take a look at one of the first techniques that we know to solve quadratic equations. And this is a situation where our middle term b is a 0. So if I had something like this, ax squared plus bx plus c equals 0, and I said let b equals 0, then it would look something like this. Notice we drop our middle term with the linear term. In fact, let's give names to each of these terms. The first term, the x squared term, is called the quadratic term, just because this is language I use a lot, and I don't want you to feel like you don't know what I'm referring to. The linear term is the bx term, and c, because it's a constant, is called the constant term. And the word term comes from the fact that you have addition or subtraction in between as your operations. All right. So let b equal 0. So you could look at something like this. You could look at something, if we put c on the other side, it might look like that. Okay. And again, I want to remind you folks that in this first equation, when you see ax squared plus c is 0, c is not necessarily positive. C is a variable. It could be anything. It's a constant, so it could be a positive number or a negative. Just like when you see this, ax squared equals the opposite of c. Don't fool yourself to saying that's a negative number. It's the opposite of whatever c is. So it's important that when you see a quadratic equation that has either of these forms, there is a shortcut method for solving it. I have a problem with the shortcut method because I've seen students misuse it over and over again and only get half of their solutions. So I'm reluctant to do this, but I will do it with you. So let's take a look at, I want to do one first that might be one you're familiar with. Okay. Excuse me, that you're familiar with, not that you're not familiar with. One like this. Okay. I also want to pull out GeoGebra for a minute. All right, and I want to show you, I'm going to take off these two. So I can't erase this because this is from my other class. And it won't even let me throw it over there for a pen. So I'm going to be bringing them back in a minute. So as you can see, this is y equals x squared minus 4. It's a quadratic equation with two variables, y and x. And if you were to graph that, notice it crosses your x-axis in two places, at negative 2 comma 0 and 2 comma 0, right? We call those the x-intercepts. When we have an x-intercept, what's the value for y? 0. So what we're actually solving is this equation. Okay, we're actually solving that equation for x. So visually, when you solve a quadratic equation that's set equal to 0, visually, you're finding x-intercepts. Okay? Some parabolas have two x-intercepts that are different. Some parabolas have no x-intercepts. Boy, it must be a very strange answer when I solve my equation and I don't get a number. What would that look like? It has no x-intercepts. Can't be 0 because 0 is a number. But what kind of numbers are along the x-axis again? What do we call all of those numbers along the x-axis? Real numbers. So what this is saying is that it doesn't have real number solutions. Voila. Aye. Aye, aye, aye. Then the other possibility is you could have a parabola that just touches your x-axis at one place, like 1 comma 0. That's a real number. And this is an example of a perfect square. A perfect square, you have two identical factors when you factor it. So you have the same answer. That makes it equal 0. That's an identical, we call them like identical twins. Even though it's one answer, we still say it has two solutions. They just happen to be identical. That's kind of a weird thing. All right. So every quadratic equation has two solutions. Sometimes the solutions are identical to each other, so it looks like one. Sometimes they're real numbers, and sometimes they're complex numbers. So when you look at this, one thing you should always try to remind yourself, if you've fallen into this trap before, is when you see a quadratic equation, circle the two and put a little note to yourself. Two answers. Now, I'm not telling you this because I'm trying to make life hard for you. I'm trying to make life easier for you because I've watched this mistake happen over and over and over and over and over again. Okay? One way to avoid that mistake is to factor that thing, because you know what? This isn't a hard expression. This expression on the left side is not hard to factor. It's the difference between two perfect squares, which always factors as +2 and -2. The factors look identical except for one's addition and one's subtraction. Those are called conjugates. These factors are called conjugates of each other. These factors are called conjugates. You're going to see that come up in a minute again. So they look the same except for one's plus and one's minus. Once you do that and you say, okay, A times B equals 0 tells me that A must be 0. So X is -2, or B is 0 when I multiply these two things. So X is +2. So notice those are the two places on my parabola, the graph I just had a minute ago, where I crossed the x-axis. Okay, so that's the visual interpretation of that answer. What happens if I have a quadratic equation like this? X squared equals -25. Okay. Well, before I get there, I want to show you the dangerous route to go. Here's the dangerous route. Does everybody agree I can take x squared minus 4 equals 0 and call it x equals 4? Does everybody agree with that? No? How about x squared equals 4? You agree with that? Okay. Here's the danger. This is what I see. Danger. Danger ahead. All right. Danger ahead. I try to be humorous. All right. Danger ahead. This is what I see. Step that teachers have left out and students haven't done for years and years and years. X can be a positive number inside that as a radicand that's being squared, or it could be a negative number. So when you say that the square root of x squared is x, and x could be positive or negative, that's untrue, because that symbol says I want the positive square root of x squared. And the only way to ensure that it's positive is by doing that. So if you do this, and then you take that equation and you say, hey, what numbers are 2 units away from 0? Well, you know it's +2 and -2. Those opposites are the same distance from 0. And that's what absolute value has to do with, the distance from 0. Now you can say x is plus or minus 2. But I tried, and I tried, and I tried to get my 096 students and my 107 students to start including this. No luck. So I'm not expecting it. Once in a while I get a surprise and I see it. So as I think it was Ramsey said, well, when you see something like this, you just got to know it's x is plus or minus 2, or plus or minus the square root of 4. All right, that's the only way you're going to have any luck. Or you could factor, and then you don't even have to remember that. Wait a minute, Tyler had a question. Tyler? Yes, yeah. Ramses?
Absolute value of -1.
Yes. Yep. Yep, Nick?
I mean, it's just another way of thinking it. Instead of doing the absolute value for the second step there, it'd be just like square root of x squared equals plus or minus.
Yes. Yeah. If you can remember to do the plus and minus, you're all set. Yes, I absolutely agree with that. Okay, so we still haven't dealt with this x squared minus 25 equals minus 25. So let's deal with that. Yeah. Yeah.
The absolute value of x, like, what would be the definition?
I'll tell you when I grade your quiz, since that was on your quiz. Okay. All right. So x squared equals the negative square root of 25. Again, it's a quadratic equation. You have two answers, and these are your two answers: plus or minus the square root of -25. And before today, you would have went, I don't know what that is, but we do know what that is now. What is it? 5i, because it's -I times positive 25, which is 5i. But remember, it's plus 5i and minus 5i. So this picture, if you were to draw it, would be a parabola that was way up on the y-axis, as its vertex, or where it turns around, would be 0, 25. That would be the y-intercept. It would never cross the x-axis. And this is what you would get when you solve a possible answer when you solve an equation like this that doesn't cross the x-axis for a parabola that doesn't. This idea we've used over and over again, the zero product property, and that allows you to take a quadratic equation, and if it's really easy to factor, why not? So you would take this quadratic equation, and as always, you want to, as your first step, you want to set your quadratic equation equal to 0, because if you don't, then you can't use that property right there. Okay, so x squared plus 11x plus 24 is 0. And now I'm going to try to make this into a multiplication problem, because I know when I multiply two things that equal 0, one of them must be 0, or both if they're the same. So I do x and 3 and 8, and I have factored that very quickly. I'm not using the quadratic formula. I'm just like, hey, that means x plus 3 is 0 when x equals -3. And this means x plus 8 equals 0 when x is -8. So if I were doing this parabola, making a quick sketch of it, I would know that that would be the two places across the x-axis, and the other place across the y-axis would be 0, 24, because of that constant right there. Okay, but I'm not asking you to graph these. I'm just showing you what it means. All right. Yes. And if it was x squared plus 11x minus 24, and it was the factors of 24 that had a difference of 11, you wouldn't be able to factor it. So that's when you have either irrational solutions or complex.
But you could, if you were like, say I got to this point on a test, and I was like, oh, stop, I can use the quadratic formula.
Sure, you can use it anytime. Yep, you can. Yep. Nope, that's section P5 dive, which you weren't here for the first 4 classes. Okay, so in general, though, you can use the quadratic formula to solve any quadratic equation. What I want to emphasize is that whenever you solve an equation, even if it's something like this, when you take this equation and you start doing things like this, okay, you solve an equation, and if you've had Norman Beebe, I know you've heard this before. You solve an equation by making an equivalent equation that's simpler. And you keep breaking it down and breaking it down until your final equation is what you're looking for. You always solve an equation with an equivalent equation. Now, why is Linda saying this? Because notice, we start off with this equation. And part of the problem in terms of time is that I can solve that equation for x without putting a single number in for a, b, or c, but just by using a, b, and c, keeping it totally general. And the method that we use to solve for x and to get this result, notice this is x equals, just like when you come down here and say x equals -2/3. This formula says it doesn't matter what a, b, and c are. As long as they're real numbers and a is not 0, I can always get the solution by following this recipe. But when you solve a quadratic equation, I want to see at the end x equals. I don't want to just see an expression. And you can kind of along the way do whatever you want. But the first step should be x equals. No. And then after, and I'll show you where the plus or minus comes in. As long as the first step is x equals, and then you just use a bunch of equal sign, fine. But I got to see an x in there somewhere because you're solving an equation. Let's do this. Oh, I forgot. My math lab asked for a solution set. So if your answer is x is 7 and x is -1, remember the set is the curly braces. You have to put your smaller number first. So you have to put the -1 and then the 7, or else it will mark it wrong. And when they were asking, like in homework 6 for coordinates, you have to put parentheses with the comma.
Yeah, it's like you're working on a graph.
Yep. Well, sometimes they just say the x, they just want the value for x or the value for y for the y-intercept. I always ask people